All right, perfect. So, hi, my name is Shiam, just in case you guys didn't know, and we have.
My name is Sunu. I'm a first year at the University of Connecticut studying computer science.
I guess I just say the same thing. I'm also a first year studying computer science and engineering at the University of Connecticut. We have two other members not here at the moment, so we'll just go ahead and go off from here. So the project we made is called iAssist, which is meant to serve as a visual assistant designed to provide real-time navigation for the visually impaired. And we use this by using multiple tools that are all AI powered. And our hope is that this will make the lives of those who are visually impaired a little easier and make them more comfortable in our world. So, this is the introductions. I'm going to skip over this for the sake of time. These are two other members who aren't here right now, but you can read a little bit about our bios. And let's start.
Yeah, so the problem we are looking to address was the inaccessibility when it comes to um, the visually impaired, where over 2 billion individuals are actually affected by visual impairments, and a significant portion of these individuals also face navigation challenges due to the high cost and limited accessibility of existing solutions. And some of these solutions, like LASIK or guide dogs, um, are remain expensive.
Yeah, sorry, just get it back here. There you go.
So our solution, iAssist, is a virtual assistant with text-to-speech functionality in real time, which analyzes and advises its user where to go and any objects or surroundings that they should be careful of. So how our application actually works is that we have a initial camera capture where the application can recognize and initialize a live camera input and then proceed. This uses OpenCV to support its main functionality. We observe the scene, which uses Ultralytics YOLO V11 for object classification, and it can distinguish between important and insignificant objects, such as like a moving car versus just like a water bottle. And finally, we have a prioritized advice, which is just a queuing system that prioritizes the most important messages that should be declared to the user, while trivial factors are left behind.
And yeah. So now to go over the actual architecture. So I'm just gonna go into a little more detail on that, and hopefully that will help those who are a little more curious about the inner workings of the project. So the way it works is that we usually have a streaming device, which in this case we often just use your phone just because that's the most accessible way to do it. And whatever's streamed through the phone will get first put in this part right here, and that's done through OpenCV, which allows us to actually take video capture. Then we use a model called YOLO, which was referenced before, which stands for You Only Look Once. It's an open source model, often used for object detection, and it performs very well in many benchmarks, and it's sufficient for our uses. So once we actually detect objects within the video frames, we then move it to and we start analyzing. In this case, we use a memory buffer where and we have two separate memory buffers. In this case, we're using a tracking memory buffer, which in this case we analyze frames within certain like a certain amount of frames, and this is a um very fast. And what we essentially do is we take the x and y coordinates and we convert this first the scene that YOLO gives us. It makes it an actual useful scene that we can actually analyze. We also look for movement detection because that's also very useful information that we would like to use for our output. In this case, we just take we find the objects and we just compare different frames, and we take the derivative and look for changes sufficient enough to alert that this is a moving object. And then once we take that and then we move it to the second step where we then take a longer memory buffer, which this in this case we call it the analysis memory buffer. This and here we analyze multiple frames, so a much larger frame set, and we actually do scene summarization. And this is done for two purposes: to make the scene have more context, so obviously it's more accurate. But also is because if you notice, we have two different threads going because this is a concurrent app where we have an LLM stream slash image analysis stream over here. We also have a TTS stream, which I'll elaborate on a bit later. So because of that, we need to align the timings just so they will line up correctly. We then use the scene summarization in the scene summarization as context for an LLM call. In this case, we actually use Grok because it's just faster because it's an inferential um, model, so it gives us faster results. So we use Llama 3.2, which is an open source model, and we do that through an Llama client to get back a very specific response. So we did a lot of prompt engineering to make sure the process and the actual navigation instructions are as useful and concise as possible. And then we make sure we have priority queue um, that first looks for keywords inside the Olama navigation instructions. And in this case, let's say in navigation, we noticed that there was an emergency, like a car going by. That would have a higher priority queue and thus would um, have higher precedence. And in this case, would be the first message the user sees compared to like something a bit more not as useful. And then once we have all this information, we actually feed it into a talk to stream system that's always running. Now, this is a much slower system, as you can imagine, because actually speaking out and um, converting the text to a speech and actually saying the message takes much longer. So in this case, we use Kokoro, which is a very high performing open source model on Hugging Face. So this is done through a Hugging Face pipeline, and it's very performant and it works really well for our use case. And after that, if everything looks good, that's the whole tech stack behind our model. There's some smaller details here and there, but this is as much as people would like to know. And one thing, if we do have time, I don't want to do right now. I could also show a demo, but I'll hear out and see what if time allows for it.
Yeah, I think we should have some time. I think you guys can go like a little bit over if you need. So
Got it. Perfect. Okay. Just give me a second. Now, I need to actually present my screen here. Actually, you know what? If you want to hear audio, I'm gonna have to. I can't. I'm not sure I can show audio if I share my entire screen. So right now we'll just see the text, but it should be fine. So this is the actual code, and just for right now, we'll just use a Python command to make this as smooth as possible. But once we run it, let's load. There. So it should connect to my actual camera, which and I hear some audio, but as you see here, they're detecting all the objects that are in my surroundings back here. And yeah, there's objects here, and then the actual instructions are being played through the audio. Because I'm sharing my screen, you can't actually hear the audio. If I can find a way to set that up, I would love to do it. But right now, that's how the actual program works.